Okay, right guys, here we go. Now, I've updated Schoology to include a whole pile of stuff for you. There are essentially 5 folders in one document. This document here, chemistry definitions. If I open it in Schoology, what I see is that it actually shows up pretty well, but it's just a preview. If you want to look at it, use it properly, you need to click on the download button. There are, I think, 4 pages in this. Those 4 pages are worth 20% or more in your exam. You will be asked to explain the following terms. What does this mean, or define? The things in brackets are options. So you can say, if you're asked what an areneous acid is, it produces hydrogen ions, which you can write as H+, or you can call them hydrogen ions by dissociation in water, or you can say in aqueous solution. And they're all there. I really strongly suggest you get your flashcards out and learn those. If I go back, here are all the organic chemistry theory presentations. They're all there. I suggest again that you go through them. What we're doing now, the organic chemistry practicals, are in this folder, and you just download them. If it asks you to enable content, you enable content. If it asks you to enable edit, then save it to your computer. All the titration PowerPoints are here. We'll start those tomorrow probably. And then there's topic by topic. This contains all the questions, not last year's yet, I haven't got them in yet, but for all other topics, all the questions and marking schemes, somewhat simplified, are there. And I think that's the last one, was it? Oh yes, all the past papers and marking schemes up to 2019 are there. They're the full department ones, but they're quite complex sometimes. There are maybe 10 or 12 ways to answer a question, and they give all the 12 ways, and you don't need those, you only need one. But they're there for reference if you want them. So there's a fair load of materials for you, which I hope you'll find useful. Right, organic practicals. We did the alkanes, the alkenes and the alkynes, and we did the aldehydes, and by inference the ketones. Now I'm going to move on to I'm going to skip one. I'm going to skip the properties of carboxylic acid because they're quite straightforward, and I'm going to go on to what my friend who he writes for one of the exam boards, the mock papers, and these are the 2 things that he reckons are most likely to come up. Now, I said most likely, not going to, most likely to come up. But you have to learn them all, but I'm going to do these 2 just in case. And they are clove oil separation and making soap. So those are the 2 I'm going to do now. So let's start with making soap. So you may have seen that soap in the shops, and you may have wondered, why do they call it palm olive? Well, they call it palm olive because they use a mixture of palm oil and olive oil to make it. That's why it's called palm olive. Right. Some of the ancillary knowledge you need for this experiment are that fats are solids and oils are liquids at room temperature. At room temperature. I'm going to underline that. Right? I'm just going to stick that up there, just to make sure that you get the idea that it's at room temperature. If you raise the temperature above room temperature, of course, fats will become liquids. You heat butter up, it melts. The second thing is that animal fats are saturated. Plant oils are unsaturated. Many of them are polyunsaturated. Remember, saturated means contains only carbon to carbon single bonds, whereas plant oils are unsaturated. They contain at least one carbon to carbon double bond. In the case of polyunsaturated fats, they contain many. Poly is the prefix for many unsaturated bonds, carbon to carbon double or triple bonds. Unsaturated fats and oils don't produce cholesterol. Therefore, they won't block your arteries as readily. So in terms of health, you should be eating unsaturated oils and fats rather than saturated ones. Now, let's look at making soap and then we'll discuss it.
Experiment to prepare a sample of soap. The manufacture of soap is one of the oldest chemical reactions known. Soap consists of the salts of long-chain carboxylic acids, for example, C17H35COONA, which is commonly called sodium stearate. Salts of long-chain carboxylic acids are made from fats or oils by the process of saponification. To prepare soap, one needs to start off with a substance that contains a naturally occurring ester, for example, cooking oil. 6 centimeters cubed of sunflower oil have been placed in a 100 centimeters cubed quick fit flask. 3 grams of sodium hydroxide pellets.
Those are, oh, I'm going to just go back a wee bit. Right, those are the sodium hydroxide pellets there. They're white and they're quite shiny because they absorb moisture from the atmosphere. You don't touch those. They are caustic. They will burn skin. These little things here are called anti-bumping granules. Anti-bumping granules are little bits of broken glass, essentially ground broken glass. And they cause small bubbles to form instead of large bubbles. You've probably noticed when boiling a saucepan at home, sometimes the bubbles can get quite large. Well, if that happens in a scientific apparatus, then it can shake it apart or damage it or break it. So we use these anti-bumping granules to produce small bubbles and stop damaging the apparatus or prevent damage to the apparatus.
30 centimeters cubed of ethanol and some anti-bumping chips have also been added to the flask.
Ethanol is there to dissolve the fat.
The ethanol acts as a solvent for the oil. The reflux apparatus was set up as shown.
Right. Water coming in from the tap goes in at the bottom. Always show that and label it as water in. Reflux is when the condenser is in the vertical position. The purpose of reflux, there are 2 purposes. One is to prevent the escape of volatile, that's easily vaporized substances, and the other is to give time for the reaction to occur. So water in at the bottom, out at the top.
Refluxing is a laboratory technique in which a liquid is boiled in a container that is attached to a condenser.
A vertical condenser.
Vapor from the boiling liquid condenses and flows back into the flask. Thus, the liquid is kept at its boiling point without loss of vapor.
And reflux means that the vapor goes up, the condenser gets to a certain point and then condenses and runs back down. I'm sure many of you have suffered from reflux when some of your stomach contents goes up your esophagus and then goes back down. That's why they're both called reflux.
This action prevents the flask boiling dry and allows organic reactions sufficient time to react. Heat the mixture over a water bath for about 30 minutes.
So it doesn't get too hot.
If we lift the flask out of the boiling water for a moment, we can see the condensed ethanol falling back into the flask. That is, it is refluxing.
You're shaking it because if any of the salts stick to the side of the flask, that will wash them back down.
After the end of the 30-minute period, saponification should be complete.
Saponification.
Allow the apparatus to cool and rearrange it for distillation.
At this time, we're going to put the condenser.
We are now going to distill off most of the ethanol solvent. This will make.
And once again, water in at the bottom, out at the top. That will normally get you 3 marks. So be sure of that. You don't need this. You don't. All you need here is a beaker to catch it's ethanol that's going to be coming out. You don't need the fancy bits.
Easier for us to isolate the soap. Gently heat the flask using the water bath.
You need a thermometer there so you know the temperature, which should be 80 degrees centigrade for ethanol. And when it starts to go above that, then you stop heating. You can see the lots of small bubbles being produced. That's what the
Continue heating until about 20 centimeters cube of ethanol has been collected.
That's about what you put in at the beginning to dissolve the fat.
Allow the apparatus to cool for a few minutes. Using the clamp to hold the flask, quickly pour the hot reaction mixture into a beaker containing 100 centimeters cubed of concentrated brine.
Brine is simply sodium chloride solution, and it's called salting out. Soap is insoluble in brine, so it immediately precipitates.
Brine is a solution of salt, NaCl, in water. Soap does not dissolve in salt solution, therefore the soap will be precipitated. The excess sodium hydroxide will dissolve in the salt solution.
Sodium hydroxide, remember, is caustic. You want to get rid of it.
Filter off the soap using a filter funnel or a Buchner flask and filter paper.
You don't need to use a Buchner flask, it just speeds the process up. So any alcohol, any water, any sodium hydroxide in solution, all passes through in the filtrate. The soap is left behind in the filter paper as the residue.
Wash the soap with fresh salt solution to remove any sodium hydroxide still present.
That's a good idea, or you can use even ice cold water will do just as well, but brine is probably better.
Using a spatula, take a sample of soap, add it to about half a test tube of deionized water.
That's deionized water is soft water. And if you mix it with soft water, You'll see it now.
Shake the test tube. We observe the characteristic lather of soap.
Right, you can call it lather, you can
soap.
call it suds, you can call it bubbles. So when you shake soap with soft water, and deionized water contains no iron, so it has to be soft, then you get either bubbles or a lather or suds. If you shake it with hard water, you get a scum of calcium or magnesium stearate.
Made looks different than the soap you buy in a shop. This is because when soap is made commercially, other ingredients like perfumes and colouring agents are added to make it more attractive.
Right, now the process of making soap, which can be referred to as saponification, is also called the base hydrolysis of an ester or the alkaline hydrolysis of an ester. I prefer the name alkaline, but I think the inspector prefers base hydrolysis. It's also called saponification. Place some sunflower oil. You can place anything you like, any fat or oil you like. It doesn't matter. You could use butter if you wanted. Into a pear-shaped flask. Doesn't have to be pear-shaped. Into a flask. You add sodium hydroxide. Caution that burns skin, so you should be wearing rubber gloves. And then add ethanol. The purpose of the ethanol is to dissolve the fat. You add anti-bumping granules to prevent damage to the apparatus. You reflux it for about 30 minutes because the reaction's slow. And reflux, 1, prevents the loss of volatile components, and 2, allows time for the reaction to occur. I'm just going to modify, well, I won't modify it, there's no room, that's why it's like that. And then you swirl to remove, during the heating process, to remove any substances stuck to the side and wash them back into the reaction mixture. And the equation is C3H5, C17H35, COO 3 times, or taken 3 times, plus 3NaOH equals C3H5OH 3 times, that's propan 1,2,3 triol or glycerol, and sodium stearate. This is the soap, sodium stearate. The apparatus you need there is set up for reflux. In the flask, whichever shape it is, you have fat or oil, plus sodium hydroxide, plus ethanol, plus anti-bumping granules, and you have a water bath so that it doesn't get too hot, and you have your condenser in the vertical position with water in at the bottom and out at the top. So you reflux for 30 minutes. Reasons: 1, it gives time for the reaction to take place, and 2, it prevents the loss of volatile components, i.e. ethanol and water, so the reaction won't boil dry. If solids collect around the edge of the liquid, swirl the flask to wash them back into the solution. Then you rearrange for distillation. Distillation, we have the condenser at a slight angle so that the liquid will run down and out. You don't need the adapter at the end, it can just drop straight off. And again, you put water in at the bottom and out at the top. You'll notice that the 2 condensers, they can be different. They can have the in here and the out can be there. It doesn't matter. In this case, instead of using a beaker of water, they're using a heating manual. This is taken from a past paper diagram. And you should have a thermometer placed here so that you know the temperature of the liquid or the vapor coming off. If it's ethanol, it should be about 80 degrees centigrade. So you let that one down and you collect it in a beaker. Any container will do. All right. So you arrange the apparatus for distillation. Distill off, can't spell, distill off the alcohol which was there to dissolve the lipid or the fat. Remember, lipids means fats or oils. And then you pour the contents of the flask into concentrated brine, that's concentrated salt solution. And this is called salting out. Soap is insoluble in brine, so it precipitates out. You filter the mixture by vacuum filtration if you're in a hurry. You rinse it with cold deionized water or salt solution, fresh salt solution, to remove the NaOH, because remember, it's caustic, and excess sodium hydroxide and glycerol stay in the solution and pass through the filter into the flask. Now, you have to learn the previous equation I gave you, but you also have to learn it in three-dimensional and full structural formulae. So, fats are what we call triesters. COOC in the middle of a molecule means it's an ester. So there's one ester bond, there's another ester bond, and there's another ester bond. That's James Bond's sister, Esther. And what happens is that is replaced by three OHs. So, and you react that with 3 sodium hydroxides, we get 3 sodium stearates. By the way, that can be called glycerol stearate. And we get glycerol, which is propan 1,2,3 triol. So you need to learn both those equations. There's a pretty high chance that this is going to come up this year, so make sure you learn it. Right? Soap lathers or form suds or bubbles when shaken with soft or deionized water. Right, there's the suds with the deionized water. With hard water, you get the formation of a scum. Right, it forms a scum, which is calcium or indeed magnesium stearate with hard water. All right, here are some questions taken from past papers. Soap is produced by the hydrolysis of vegetable and animal fats. A, what is the principal chemical difference between vegetable and animal fats? And then a sample of soap was prepared in the school. Well, let's give you the answer to that. Right? The chemical difference is fats are saturated, all single bonds, or you can say vegetables, fats are unsaturated or contain double bonds. 5 marks for that. A sample of soap was prepared in a school laboratory as follows. Approximately 3 grams of lard, that's animal fat, 2 grams of sodium hydroxide, that's an excess, and 25 cm cubed of ethanol were placed in a round bottom flask. A condenser was fitted to the flask and the mixture was refluxed gently for 20 minutes. Diagram 1. Following the reflux, the apparatus was allowed to cool slightly and the arrangement of the apparatus was changed so that the ethanol could be removed by distillation. Diagram 2. The residue from the distillation flask was then dissolved in a minimum of hot water and the solution decanted into a 75 centimeter cubed of brine. The soap was then isolated. So, apart from the lard, sodium hydroxide and ethanol, what else should have been placed in the reaction flask prior to reflux? And why was the mixture refluxed? And why was the ethanol added? So there are 3 questions there. What else was added? Anti-bumping granules. Once you get anti-bumping, that's the important bit. Why reflux? Because the reaction is slow, or to complete the reaction, or to boil or heat without losing volatile components or volatile material or ethanol. Just one way is all you have to say there. 3 marks and 3 marks. And then what was the purpose of the ethanol? It was a solvent for the lard. Why was it desirable to remove the ethanol after the reflux? Well, it's easier to isolate the soap, or it avoids waste of ethanol, or it maximizes the yield. Well, that's two answers required. Easier to isolate the soap and maximise the yield. The first correct answer gets 3 marks. The second correct answer gets 3 marks. Right? And then D, why was a minimum of hot water used to dissolve the residue from the distillation, and what is brine? Well, the minimum is to maximise the precipitation of soap, and brine is concentrated salt solution. The C is often referred to as the brine or the briny. E, describe how the soap could be isolated from the mixture of soap and brine, and give one precaution that helps to ensure that soap is free of sodium hydroxide. Well, precaution, wash it, well, to remove it by filtration. You don't have to say vacuum filtration. And precaution, wash it with ice cold water or ice cold brine. Why ice cold? Because soap is less soluble in cold water than hot water. You know that from practical experience. And here's another one. A sample of soap was prepared in the laboratory by refluxing a mixture of approximately 5 grams of animal fat, 2 grams of sodium hydroxide pellets and excess, and 25 cm cubed of ethanol in the apparatus, like that drawn on the right. Why was the reaction mixture refluxed? Name the type of reaction which occurs during the reflux stage of this preparation. And B, complete and balance the equation below for the reaction between glycerol tristearate and animal fat and sodium hydroxide. Well, the first answer, why was it reflux? To speed up the reaction or to maximize the yield. And it says allow to prevent the loss of vapor, ethanol or solvent, whichever you want. And the type of reaction, it's either the base or alkaline hydrolysis or saponification. Notice that base and alkaline are not actually required, but I would always give one of them anyway. And complete the equation, it's C17H35 COONA and CH3, or well, you can write the equation. It has to be structural, so you can actually draw the structure, or you can write it as CH2OH, CHOH, CH2OH. That gets you 3 marks. And balancing it, putting the 3 here, well, the 3's there already, so putting the 3 in front of the sodium ethanoate, or the soap, gets you the next 3 marks. What is the purpose of the ethanol? Why is it desirable to remove the ethanol after reflux? Describe with the aid of a labeled diagram how you would remove the ethanol after the reflux stage of the experiment. So, purpose of the ethanol is a solvent. Why? It's easier to isolate or extract the soap or to avoid waste of ethanol. Describe, well, a diagram, any 2 from the list below and 1 correct label, 6 marks. So there's the diagram. You didn't put in a Bunsen burner, you can just put boiling water, that would do. The Bunsen and thermometer in the correct position, right? And the thermometer, don't forget the thermometer, or gentle heat, a water bath. The still head and distilling flask, that's all of that. The condenser sloping down, and inlet and outlet for water. Water in, water out. Notice that the connections are on opposite sides of this particular condenser. And then it doesn't, they can both be on the same side. It doesn't matter once you show water in at the bottom, out at the top. And a collection vessel. Right? So they've got a test tube here. This, called an adapter, is not required. The diagram with any 2 from the list above and no correct label, 3 marks. So you've got to label at least once. And then D, describe how the pure sample of soap was obtained from the reaction mixture. Dissolve the residue in a minimum of boiling water, pour onto the brine or into the brine, filter or wash with a little ice water. And E, at the end of the experiment, what is the location of the second product of the reaction? That's glycerol, and of the excess of sodium hydroxide. Well, the second product is in the filtrator in the Buchner flask, and the sodium hydroxide is in the filtrate or the Buchner flask. But there are two questions, so you have to give two answers. You can't just say it once and say it's done. Give them both. What would you observe upon shaking if a little soap prepared in the experiment is added to a test tube containing deionized water, a test tube containing mineral water from a limestone region? Well, in the first case, you'd get an immediate lather, you'd get suds. In the second case, you'd get scum or no lather. Either will do. Now, has anyone got any questions on that? Please send them to Fian.
No questions as of yet, Peter, but I'll let you know when you come in.
Okay, that's fine, just in case there are any. As I say, it's pretty important that they learn this one, and that the equations, although they seem difficult, they're not quite as difficult as they seem, because if I go back up to this one, you're simply writing that, and then that again at the bottom, and then in the center you're writing it again, but with just one H. And again here, you've just got that one. It does take a wee bit of practice, but once you've learned it, it's quite easy. Okay, I'm going to head on to the next one. Which is the extraction of clove oil. Now, the point I made about these are the two most likely to come up, but they're not guaranteed. The inspector goes out of her way to make sure that people can't predict what she's going to ask about. So the second one is the extraction of clove oil. Right? This is the apparatus that we use. Now, this is a fancy apparatus. You don't need anything as fancy, but you could just bring your condenser and stop your condenser there and put a beaker here. So what do we have? Note that this tube here, right, the safety tube, and label it safety tube, goes under the level of the water. This yellow thing here is water with anti-bumping granules. Oops, sorry, with anti-bumping granules. The purpose of this is to stop pressure build-up, which could possibly cause an explosion. This is a steam generator. It produces steam. If it gets too empty, you can stop, disconnect, fill it up again, and start it going again. It passes steam into this flask here, which can be any shape you like, but this tube has to be under the water surface. In it, you have cloves. We use whole cloves, and here's a picture of whole cloves. They're used in cooking quite a lot for apple pies or for your bacon joint, for your turkey and ham. And these are little flower buds which are just about to open, and they're harvested at that point just before the buds open and dried, because that's the time when the concentration of clove oil, which is properly called eugenol, is at its highest. That has been asked. So you bubble the steam in here. That gets this up to the boiling point of water. It lowers the boil. The whole point of this process, called steam distillation, is that it lowers the boiling point of the substances present, so that they can boil off at a low temperature. If we had to do it dry, the temperature required to boil them off would be so high it would damage many of them. And again, water in, water out. Water in at the bottom, out at the top. All right. Clove oil is used in a flavouring for clove rock. I'm sure many of you have seen and tasted clove rock. It's also used as a painkiller, but not the pure oil. The pure oil burns. And you can buy a diluted version in the chemist. If you have a toothache, you can drop it on your tooth and it numbs the toothache to some extent. Steam distillation is used as some components have high boiling points and a high temperature needed to distill these could cause damage to the other components. Buds are used because the oil content is highest at this stage. You have to have a safety opening to prevent explosion. Make sure the safety tube of the steam generator is below the water surface. The steam generator plus anti-bumping granules, that's my ABGs, is my shorthand for anti-bumping granules. Write the words anti-bumping granules. After 30 minutes, disconnect the steam generator to prevent suckback. That's not really very important, but they expect you to say it, so say it. And then collect the pale, milky emulsion. The pale, milky emulsion, you can call it pale, milky distillate if you like. Here is an example of it, right? An emulsion is droplets of oil suspended in water, right? Then we have to separate the eugenol. In here, we've got the little droplets of eugenol suspended in water, what we call an emulsion. We have to get rid of it. So how do we separate it? We shake the emulsion with cyclohexane in a separating funnel. This is a typical separating funnel. It's wide at the top and narrow at the bottom. And you do it with venting. What that means is loosening the lid. It's like a bottle of 7-Up. If you shake it, gas comes out. Well, if you shake eugenol with cyclohexane, there is some vaporization, pressure can build up. So you simply loosen the stopper at the top, just slightly to let any pressure off, to allow vapor to escape. The eugenol dissolves in cyclohexane. Eugenol dissolves in cyclohexane. And you allow it, you sit it and allow layers to form. Here is the cyclohexane with the eugenol dissolved in it. Here is the water. Right? So that's eugenol dissolved in cyclohexane. That is water. You remove the water, you open the tap. Here's the tap, you open the tap, the water comes out first, and when it gets to right there, now you can't actually see it, you can see it get to there, but you have to allow that wee bit there. When it gets to there, you close the tap, you take away that beaker, you put another beaker in, and you collect your eugenol and dissolved in cyclohexane in the second beaker, and you evaporate the cyclohexane in a fume hood. You'll be left, and that would probably be overnight, you'd be left with eugenol. It smells lovely, but it's corrosive, it will burn you, so wear rubber gloves when you're handling it. And it's used as a flavouring, clove rock, and as a painkiller. I've said that already. Now, you need to know the structure of eugenol. You need to know it. It's an aromatic compound. It contains a benzene ring. The benzene ring is shown in red here. Now, you can replace it, 3 double bonds with of course, with a delocalized pi bond. And remember that this is the simplest way to draw the structure. You've got a carbon at each bend. At the end of each bend, each one you've got a carbon, and there's a carbon-carbon double bond there, and then you've got an OCH and a single bond to an O and an OH there. There it is as a stick model, right? You need to be able to draw its structure. So it takes a bit of practice, right? It takes a bit of practice, but not too much. So for goodness sake, learn it. All right, now steam distillation of clove oil. Let's have a look at this. Again, the apparatus used here is a bit fancier than most places would have. They use a copper steam generator.
Experiment. To extract clove oil from cloves by steam distillation. In this experiment, steam distillation is used to extract clove oil from cloves. The main constituent of the oil found in cloves is a substance called eugenol. This is an aromatic compound containing a benzene ring. Set up the apparatus for steam distillation as shown. Steam is produced in the steam generator.
Well, that's just a fancy one, don't worry about it.
The steam generator is fitted with the safety tube to prevent build-up of pressure.
Notice that it actually bends over and down so that if hot water does come out of it, it's going to spray down the way, not up over you, but it doesn't really matter in terms of the exam, that is.
The steam trap collects any steam that is condensed to water.
Well, that's not
If
vital.
the steam trap were not present, the flask containing the cloves would quickly fill up with water from the condensed steam. The flask in which the cloves are placed is part of the usual distillation apparatus.
Again, water in at the bottom, out at the top.
About 1.5 litres of boiling water have been placed in the steam generator.
Amounts don't matter for the exam.
The safety tube and rubber stopper have been inserted into the steam generator. We have ensured that the bottom of the safety tube is well below the level of water in the steam generator. About 5 grams of whole cloves have been placed into the pear-shaped flask. 10 centimeters cubed of water has been added to the pear-shaped flask. Turn on the hot plate and pass steam through the flask until a sufficient amount of the clove oil emulsion is carried over during the distillation.
You can see the steam bubbling through the cloves there. You can do the same with lemon to get lemon essence, or orange peel, or lavender. It's a very common
Note that
process.
the emulsion has a milky colour. From time to time, we may also have to empty the steam trap of water.
Don't worry about the steam trap. It's not essential.
We notice that the white milky coloured liquid is being extracted from the cloves.
And again, you don't need the adapter at the end of the condenser.
We hope that you also enjoy this nice smell from the steam distillation that you have carried out. The emulsion has a really nice smell of cloves, and we invite the rest of our team to sample this lovely smell.
And they're all doing it wrong. They're all sticking it straight to your nose. You never stick anything in the laboratory straight to your nose. You waft it towards your nose. Why are they all there? Those are all the people that were involved in making the various videos. Oh.
Fantastic. Jamie, take a bowl.
Right, here's some past questions, and there are more in topic by topic if you look there. The diagram shows the arrangement of glassware for the extraction of clove oil from cloves by steam distillation. What is the purpose of the tube marked X? What is collected at Y? Describe its appearance. state one use of clove oil. Notice that the one is in bold. So it prevents explosions. Two, and notice if you say safety, that's not enough, right? And two, what is collected at Y? A mixture of clove oil and water, or a clove oil water emulsion would be fine. Describe it: cloudy, milky, not creamy. Why they won't take creamy, I don't know. It looks like cream to me, but there you are. Or white or emulsion. And three, one use of clove oil as a flavouring or a local anaesthetic. Now you can say it dulls toothache. That would be the same as saying local anaesthetic. The diagram shows the apparatus suitable for steam distillation. What natural product did you extract in the school laboratory using steam distillation? Right? Clove oil, or eugenol is its proper name. What is the appearance of the material collected during the steam distillation? Cloudy, milky emulsion, except white but not clear. What substance distilled across along with the natural product? Water, of course. Identify one safety feature of the apparatus drawn. Explain how this feature contributes to the safe use of the apparatus. That's two questions, right? So the safety tube, and it releases pressure to prevent an explosion. Now, this is one dealing with the separation. Diagram B shows a separating funnel in use in a liquid extraction of clove oil from the emulsion produced in a steam distillation of cloves. What is an emulsion? Right? It's oil droplets suspended in water, or a colloid. So that or should be in red. Name a suitable organic solvent. Name a suitable organic solvent for use in the liquid extraction of clove oil. Well, cyclohexane is the one to give for that. There are others, but cyclohexane. Other than wearing eye protection, gloves and a laboratory coat and tying back long hair, state one safety precaution that should be taken when using a separating funnel. Remove the stopper regularly, or in a fume hood. Now, remove the stopper regularly, venting would cover that. How is the clove oil isolated following the liquid extraction? You evaporate the solvent, right? And then 5, steam distillation and liquid extraction were used to isolate 0.15 cm cubed clove oil, density 1.05 grams per cm cubed, from 5 grams of clove oil. What is the percentage yield by mass of clove oil? Now, this is a favourite type of question in the organic practical. If you're given the density and volume of something, you work out its mass by multiplying the density by the volume. So it's 0.15 times 1.05, right? And that equals somewhere either 0.1575, or you can take it to 0.16 if you like. And then that was out of 5 grams. So your yield, your percentage yield, is what you actually got, which was this 0.1575 out of how much did you have? 5 grams, and multiply that by 100 to make it a percentage, and you get 3.15. 3.15. Now, are there any questions on that one?
No, nothing in there yet from me anyway.
We're all very shy. Right, now I think that's about time up. Now, there are a couple of other experiments that we could cover there in organic, but we've covered the main ones. I think it's it's reasonably unlikely that formation of benzoic acid will come up, but it could come up, so don't forget it. So can we do a poll and see, do we want to go on to titrations? As far as titrations concerned, my friend reckons the most likely candidates are the amount of iron in an iron tablet and a bleach experiment to determine the concentration of bleach in the liquid. So what do you want to do next class? Do you want to finish off organic